All right, we're going back in time. Okay, so before 1900, scientists believed that the energy is not quantized. Here's what I mean by that. The energy that can be gained or lost by an object could be any number. For example, if you heat up an object, let's say this is heating iron, the let's say an iron can obtain the energy. It could be 1 kilojoule, could be 1.1 kilojoule, could be 1.11 kilojoule, could be 10,000 kilojoule, 1,000.125 kilojoule, whatever number that is, could be any number. All right, so that energy is not quantized or continuous. That's what they believe. Right, and if that is true, the energy that's coming out right here, let's say if you heat up the let's say a sodium, right? So sodium, the flame that's coming out, if you put this light through prism, you should be able to see rainbow, like a band. Okay, but in reality, no. Like if you heat up sodium, you see a line spectrum. I'm sure you talked about it before. A hydrogen 4 line. See that? It's not like a band like that. So the energy is not quantized, but no one's believed that at the time. Okay, this is like way before 1900. And until the first person, a young, handsome, smart scientist, starting a new era in physics, right? This is about in 1900. And so a German physicist named Max Planck, we talked about this guy a few times already. He was analyzing the energy that coming out, that he heat up the energy, and this he heat up an object. This object releases energy. He analyzes this energy. Right? He found out that the energy that an object that release, it got to be only specific number. Right? If you heat up at the low heat, for example, the iron turn to be red color. If you heat up higher, the iron absorb more energy. The energy that coming out turn to be yellow color. More energy turn to be a kind of orange color, and that's all the iron can do. You never seen an iron a heating iron show a rainbow color. No, that's weird. You never seen that. That's not true, right? And that's the reason why hydrogen can release a certain amount of energy. Only for energy, that's it, right? And so he said that atoms and molecules can emit energy only a certain discrete quantities called quanta. This is what we call quantum, the quantum theory. And when he came out like this, I published this paper about quantum. The energy is not quantized. The energy is quantized, is a discrete number, not continuous that they had been believing. Other physicists got mad at him, throw him. If there were an internet, his Instagram probably got shut down. Too many bad comments on him. It's real. People got mad. It's like slap like a scientist in the face and say, "Hey, believe me, the Earth is flat." What do you think? Well, that's not true. No one believed that, right? But he actually said something like that, but he got the proof because it's not really true. Okay, and here's the quantum theory in a nutshell by Max Planck. It goes like this, right? So Max Planck looked at the energy as a particle called photon, right? So he looked at the energy, which is, we call it as a wave, not a particle, right? But he said energy can be viewed as a particle called photon, a little thing, little particle called photon, okay? And E equal to h nu. You know where that's come from. So he came up with that that equation, right? H nu, that's the smallest amount of energy, H nu. Okay, so the smallest energy that can be gained or lost by an object is called quantum, okay, or H nu basically, or plural is quanta. I'll give you an analogy here. The smallest amount of money you can transfer, you can do transaction is 1 penny. That quantum, okay, quanta, that's plural. And you can exchange when you want to transfer, you can exchange the money. You exchange your money as the multiple of penny. For example, if you wanna Venmo or Cash App your friend, let's say $1, that's 100 times of a penny. If you wanna transfer $10 to your friend, that's 1,000 times of a penny. Does that make sense? So Planck said the energy that can be gained or lost only in whole number multiples of the quantity h nu. So it's going to be 1 h nu. So look at it right here. So Tusky can gain 1 h nu, could be 2 h nu, could be 3 h nu, 100, 1,000, 10,000 h nu. Right? The h nu is the smallest amount of energy that can be transferred, called quantum. Now it could be multiple, and an object could be gain or lose the energy by the multiple of quantum. Basically, that's what he said. All right, and also he adds that light, like the wave, can be viewed both as wave and a particle. The particle called photon. Okay, so the light had the wave particle duality. It could be both way. In 24 years after quantum theory was published, so in 1924, we have a French, I think, physicist saying that any object could be viewed as a wave or particle, everything related. But is that object gonna be more like wave or behave more like an object? Like for us, we behave more like object, more like particle. But for the small particle like electron, it will behave more like wave. I look at right here. This is his equation. Not going to be on the exam, but I just want to show you. So mass and Joule is velocity, and that's lambda, right? So he related mass, which is a particle, a property of particle, and the wavelength, which is the property of wave. Together, they are directly inversely proportional. If you are really heavy, you have low wavelength. You more like particle, not like wave. Electron, who has wavelength, right? Small have wavelength, really light, so behave more like wave. Okay. All right. Now, using the quantum theory, how do you explain the 4 line spectrum of hydrogen? Let's talk about it on the next video.